lecture เมื่อวานเนาะ yesterday's lecture we have some introduction about the statistic types, and I make an introduction a little bit about the descriptive statistic and inferential statistic, and we start talking about descriptive statistic, that it is the number that actually explain the feature of the data set that we have, and we talked about, I introduced to you two of the measures that is important, which are central tendency, which has the members of this group are means, median, and mode, and we know the difference between the two, and we have some practice just to make sure that you could identify the three types of the central tendency. And we have gone through some of the measure of the spreading of the data set. Okay, so it's the measure of dispersion that has range, mean deviation, and standard deviation, which are the values that we probably use the most together with mean, because we normally express our results in mean plus and minus SD or plus and minus errors. So those are the two important stuff. The lecture today, I will talk about the other two features of the data that is included in the descriptive statistic. Okay, and okay, and the first one, I mean the third, okay, following the mean, the dispersion or the deviation, the third measure of the third descriptive statistic, or the third features of the data set, is the asymmetry. Okay, is asymmetry of the data. This one is more or less it's describe how the data acts. Okay, so it's describe how the distribution of the data looks like. Okay, so it's the measure of how the data spread, whether from the mean values, which is the central values, how it's spread left side and the right side of the mean values. Okay, so in order to explain those type of data, there are two terms that come into play. The first one is the skewness. Okay, the skewness. A skewness is a distortion or the asymmetry from the symmetrical bell curve. Okay, maybe you could be you can remind yourself about a normal distribution curve, which is a bell curve, more or less, or something like these pictures here. Okay, so the skewness tells you whether shape of the curve is symmetrical. Okay, and another term is kurtosis. Kurtosis tells you that whether the curve is widely spread or whether it's narrowing together. Okay, let's see the skewness first. Okay, the skewness, as you can see, that if the curve is in symmetry, so there's no skewness, just as the normal curve. So you have the mean, median, and mode at the same point. Okay, so the average is in the middle, and the middle data is also in the middle. Okay, so the value itself is in the middle, and also the mean data is the most frequent. Okay, so normally with this type of curve, the plot would be between numbers of data, okay, here, and the value of the data, which is here. Okay, so it's the frequency of the data and the value of the data. So actually, the skewness, okay, it actually has some formula to calculate the skewness. I didn't put the formula in, but you can search the internet if you are in need of explaining how your data is distributed and you want to use the skewness values. You can search for the internet. There are so many data. Okay, the point here is I want you to know that with the data distribution, there were 3 types of the data distribution that could happen. Okay, so if the thing are the data are within the normal curve or normal distribution, it has no skewness, so it's symmetrical. Another type, one of the type that could happen is the negative skewness. Okay, the feature of the data with the negative skewness is the pictures here. Okay, it's a picture here. So what you see is it sort of like focuses on the right hand side. So it's negative skewness because it's skewed down on the left hand side, which on the negative side of the curve. Okay, and the feature of the negative skewness is that if you see the curve, the mean, which is the average, right? The average would be on the most left. Okay, and you know that the highest point are the mode. Okay, or ฐานนิยม. So it's the most frequent data, most frequent values that happen in your data. So the mode is on the top here. Okay, so it's skewed to the skew was on the left, which is a negative skew, but the curve was sort of like moving to the right. Okay, so the median, which is the most middle data, mean is the average, median is the central data when you arrange the data in series. So the middle point is there for the median. Okay, so that is the feature of the negative skewness. Okay, another type of skewness, which is the opposite of the negative skewness, is a positive skewness. So you can see that the graph, the distribution of the data was like moving toward the left. It is positive skewness because the skew was sort of on the positive side of the curve. Okay, again, you can identify the values of the mode, the median, and the mean from for the mode is the most frequent occurred data. So it's on the highest point here. Okay, and the median is the middle data. Okay, and the mean is the average. So this type of thing happens with the different skewness. So you should be able to identify the central tendency, each type of central tendency in this skewness. This type of distribution, okay, so this is, you probably know very well about the normal distribution. So it's symmetry, and the positive skewness is somehow what we probably see a lot also in inferential statistics, because it is the shape of the F distribution curve. Okay, we will cover about those distribution curve and how it plays its roles in inferential statistics when we actually do that next week or the week after. Okay, so that is the skewness. Okay. The next measure of the asymmetry of the data is called kurtosis. Okay, so the kurtosis is telling how widespread it's a symmetry things, but it tells how widespread the data are. Okay, and different type of kurtosis is shown in this picture. Okay, so normally with the kurtosis, we are having a normal distribution, which is the sort of like a reference point, how the kurtosis is called normal. Okay, so if the data is normally distributed, it's called mesokurtic, or it's a normal distributed. Okay, if it is flat, okay, if it is more flat, it's called platykurtic, and if it is more peaked, like on the blue graph here, is called leptokurtic, which is more peaked. Okay. So the most frequent distribution that we come across are the bell curve of the normal distribution curve. Okay, and its importance is that most statistical assumption was based on the normal distribution. So whether you are doing the statistical test or doing something which is not using like the F distribution and that type of stuff, they are normally say that, okay, it's normally distributed data. Another type of curve of the kurtosis that you see a lot is a T distribution curve. Okay, so if some of you have done some sort of T test, okay, to compare the mean of the two set of data, is a T distribution curve. Okay, the point is that T distribution curve is not a normal distribution curve, so it's more peaked, but it is getting closer and closer and closer to normal distribution curve when your number of sample is high. So normal distribution curve, if we think of it, is that it's supposed that the whole populations are normally distributed. Okay, so but for T distribution curve, we only take like some sample of data, okay, some number of data, and that's why when the number of sample is getting more and more and more and more, it is getting closer to a normal distribution curve. Okay, and I would like to talk a little bit about the feature of the normal distribution curve. Okay, sometimes, okay, probably maybe you have heard that when some subjects, when they are grading the students, okay, they probably say that, okay, the average of the class would get C+, like the grading system. Okay, and if you are going to get B, you will have to be higher, like one standard deviation higher than from the mu, and if your mark is within 2 standard deviation higher, you get B+, and if you are in that case, you get like A. Likewise, if you are 1 standard deviation lower than the mean, you probably get C, or this one get D+, and that type of stuff. Okay, and since this is a normal distribution curve, so you know that it's mesokurtic. Okay, so mesokurtic is normal distribution curve. Okay, and this is the feature of the normal distribution curve. Okay, so the important features is that if 68% of the population is within this standard, the area, and if the area under the curve here is 68%, okay, and the area within this curve, I should probably, okay, should probably write down. So for example, okay, it's going to be normally distributed. I mean, the data is going to be normally distributed if the population within this red area is 68% of the population. Okay, so this is one thing that happens. So within one standard deviation, and also %95 has to be within 2 standard deviations. So that means that if the population of the blue area and the red area add up to 95% of the population, okay, so that's the second thing that you can say that, oh, it's probably be a normal distribution. And if all the areas together, the green, the blue, and the red area, contain 99.7% of the distribution, it's I mean, all these three will tell you that it is a normal distribution. So that's how you could identify like how a distribution is a normal distribution or is not a normal distribution. It could be T distribution, which is elliptokurtic or platykurtic. So it's only be normally distributed if these 3 points are checked. Okay, so it's sort of like having some features. Okay, and what I talked earlier is that, say, I mean, the easiest example that I see as a teacher is that if you have a lot of students and the grading system is by group or not by mark ก็คือเป็นการตัดเกรดแบบ in กลุ่มไม่ใช่ in เกณฑ์ so normally they get the average of C plus. If you get the mark here, you get like from here to here you get C plus, from there to there you get C, and that sort of stuff. Okay, the point is that when another point that I want to talk about is that when you are thinking about kurtosis, okay, when we're talking about kurtosis, most of the time it would be on a normally distributed curve. Not normal distribution, but the symmetry curve, the symmetric curve. So if it's not symmetric, it's not, you probably cannot like use kurtosis to explain the data, only the skewness. Okay, the point is that how are we going to make use of this data? Okay, I want to give you some example. Sometimes when you are when you want to present something and okay, let me give you sort of like a real example. Okay, maybe it's easier for you to see. Okay, so for example, if we go back to this salary of the employee in the company, okay, and if you want to see how the data is spreading, okay, you want to find how the what should I say, how the salary is distributed within the company. Okay, so you have 10 people, right? So basically you have the people who get 12K salary, you only have 1 people, correct? And the next one is 14K, you have another 1 people. Another one is 15K, the salary. 15K, you get 1 to 3 people. 16K, you get 1 people, get 16K. Okay. What else? 17K, you have another 1 person. 18K, you have another 1 person. And 90K, okay, jump to 90K, you have 1 person. And 95K, you have another 1 person. If you want to sort of like see how things are distributed, okay, you can set up like a curve. This is like the frequency of how things happened, and you can say this is a salary. Okay, so you have the salary of 12K, right? 15K, say, okay, 16K, 17K, 18K, you have 14 here, and you have like 90K and 95K. Okay, so this is not to scale, okay? So you know that this one you only have 1 people here. 14K, you have another 1 people here. 15K, you have 3 people here. 16K, you have 1 people here. 17K, you have another 1 people here. So this is like 1. This is like 3. Okay. 17K, you have 1. 18K, you have another 1 here. 19K, you have another 1 here, and 95, you have another 1 here. So basically, if you like this curve, okay, if this is the curve, you see that it's the right skewness. So it is, okay, it looks just like a positive skewness. Okay, sometimes presenting the results doesn't have to be average and SD all the time. Okay, it could be something like this as well. Okay, I personally use this type of distribution in some of my, to presenting some of my data as well. Okay. For example, in one of my in one of my paper, okay, in one of my publication, I'll see if I could find it quickly. In one of my publication, I use sugarcane bagasse, and I'm not like selecting a specific size of the sugarcane bagasse in my research, but I want to say that, okay, whatever I have, okay, from, okay, I see it. I'll see if I could share this to you. Okay. Hold on, can you just bear with me a little bit? I want to show you this so you have some idea of the choice that you can actually use this type of data to show people something. Okay, so okay, this is the publication that I talked about. Okay, okay, okay. I use sugarcane bagasse in my research. I don't sieve and only select one part of the bagasse to say that, okay, I'm using bagasse of this size and that size, because I feel like whatever I get, I use all of them. So one way to to make my data more meaningful, not just say that, okay, I use as I receive. What I did was I saving and dividing the distribution. Okay, you see that I have like the size distribution of my sugarcane bagasse. Okay, initially I make a graph of this table, but it's a regulation of the journal that I cannot have more than how many figures, so I have to change this into tables. But if you see here, one way that I do is that I have the size distribution, not only one size, because when you see, you get a range of size of the thing. So you see that it's if you plot the graph, okay, if you plot this curve, okay, you see that this one would be weight percent and that one would be size range. Okay, and what I have is I have less than 0.105 here and blah 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 until there. So what I have is I have something like this also, if you see. So it is one way that you can use the distribution curve to actually explain the values or the data that you have. Okay, so that's one way that you apply this knowledge to your own work. Okay, right. So that is what it is. Okay. Okay. So we have done 3 measures of the descriptive statistic, the features of the data in descriptive statistic. Okay, just to remind you that we're talking about the central tendency. We talked about how spread the data is, and what we just finished here is the measure of the asymmetry of the data set that we have. Okay, and the last features of the data that you can use descriptive statistic to explain is the measure of relationship. Maybe the measure of the relationship is another one that you probably use most frequently, especially if you want to fit curve and that type of stuff, or finding a model solution, the model equation. Okay, basically it's R squared. That's what you know most. Okay, before we go into those details, when you go into those details, okay, actually for Thai student, okay, for Thai student เวลาบอกว่า measures เนี้ยมันไม่ได้เหมือนกับการวัดนะคะ measures นี้ก็คือเป็นการบอกว่ามันเป็นยังไงนะคะ okay. I just want to make sure that you understand when I say the measure of the features of the data, okay? Because it's a common words, but you probably get confused. Measure of features of data. The point is that every data set has a features, okay? And the measure of the features means that it's the way you tell how the data, what are the features of the data. So it's just like when you are measuring like the length of the pen, you measure it by using what, ruler, right? Just to tell them how many centimeters they are. But for the data, you can't do something like that, right? So it is the way to tell the features of the data, just like you say that, okay, the feature of this pen is the length. You use the ruler to measure the length. of this pen, but for the data, these are the values that you can explain the data. Just like this pen is 20 centimeter long, but like the set of data, you can't just say, okay, this data, well, you probably can say it's like 10 data, but really to tell the features of the data, these are the three things, okay? Central tendency, how the data disperse, how asymmetry or how symmetry it is, and also the measure of the relationship or the correlation. So it's the characteristic of the data, what you can use to explain the characteristic of the data, okay? Okay, so, okay, let's move to the last thing that we could use to explain the characteristic or the features of the data are the measure of relationship. Okay, so when we have like a set of data, one set of data, or if you only have one variable, of course, there's no relationship, right? Because if you think about the word relationship as a relationship, you have to have more than one people, okay, in that case, okay? You can't marry with yourself, you have to marry with someone to have a relationship, okay? So that's the easiest way to, that is the easiest way to see it. Okay. So if you have one variable, of course, you don't have a relationship, okay? Relationship comes when you have more than one variables, okay? If you have what we call a bivariate population, so it's two parameters, two variables, then the relationship may exist or may not exist, okay? And also with multivariate population, the relationship may exist. I'm using the word may because it's not necessarily that you have two set of data or two variable, and those two variable has to have a relationship. Okay. So for bivariate population, it is probably something that you see most. Like it's when you having like plotting a graph between X and Y. So it's two variable, right? So that means that you have a graph, the Y and the X, and you plot and see if there's any relationship happens, okay? But like for multivariate population, if you are not doing some sort of modeling, maybe you will not come across that. But if you, maybe you have seen in some of your friends' work, if you go to like a seminar that your friend give, and they are doing the RSM, right? The response surface methodology, and then finding the surface, having equations that explain the surface. So that exists when you have more than two variables. So basically, if you have two variables, when you plot graph, you have X and Y. But if you have more than two variables, you are likely to get like 3D graph or 4D graph. Okay, so it is something like that. So if make it like easy, if you have two variables, you can have, if you plot a graph that explain the relationship, you plot X and Y, basically X and Y, because it's only two dimension, right? But if you have multivariate variate population, you have more than two variables, then you start having like 3D graph, right? You start having 3D graph, you have X, Y, and Z. So when you have something like that, so it's more than two variables. Okay, let's see. In telling the relationship, there were two words. You probably see those two words in correlation and the word correlation and regression. For Thai students, if you open the dictionary, when you open the dictionary, it's the correlation and regression. Maybe the translation is similar. Correlation อาจจะเป็นความสัมพันธ์ regression เป็น regression ส่วนมากใช้ regression เนาะbut they are different. Okay, those two words are different. Okay, correlation will tells you how the two variables tend to change with one another. Okay, but regression and cause effect relationship. So the regression, the word regression normally involved with fitting data points with equation. So that's when you have regression. Like linear regression is when you are trying to fit linear curve or linear curve basically. Okay, but the correlation is something that tells you like if you change X, whether Y will change. Okay, but it's not a cause and effect. Okay, it's just tell how correlate these two are. So if X change, how likely is Y going to change? Okay, but regression is something else. Regression is about fitting the line to data pot. Okay, so for regression, you use the relationship to predict something from something else. Okay, but correlation tells you how these change together. Okay, so just for explaining each point, the correlation say how strong the two variables are related. Okay, so if X change by 1 unit, whether Y change by 2 units or another way around, or if X change, Y doesn't change at all. So that's how the correlation is. Okay, when we talk about correlation, we are not talking about fitting a line through data points. Okay, but there are a word called the correlation coefficient. Okay, it's a coefficient that tells how much a variable change with the change in another variable. Okay, we have examples, so maybe it'll be a little bit clearer when we go through the example, but we are going to just talk through it first. Okay, so the symbol more or less for correlation is R, which is very close to R square, right? Okay, R and R square is different thing. If you only see R, is likely to be a correlation, but R square is something else. Okay, because R square is obtained from different calculations basically. Okay, if the correlation is equals to 0, that means there is no relationship. So change in this thing doesn't affect the other thing. Okay, if you have R more than 0, which is a positive values, then you have positive relationship. That means that positive change in these values cause a positive change in another another value. So these two values these two parameters, has a correlation, has a relationship. Okay, R less than 0 represent the negative relationship. Okay, So the change in these values cause these values to decrease. Increase in this one cause a decrease in that one. Not increase in this one cause an increase in that another one. That was a positive relationship. Okay. So that is the correlation. But like I told you, regression is a cause and effect relationship. That means that when we are talking regression, we are talking fitting the data point with a line. Okay. We fit the line because we want to predict something. So that is a regression. Okay. Today we will talk correlation, and on Thursday we will cover the regression, and you could probably see how they are different. Okay, so for correlation, there are many types of correlation as well for different type of data set, the two data sets, since you can have relationship or you can have like correlation or regression when you have more than two sets of data, right? The first correlation that I want to talk about is a Spearman coefficient. Okay. Spearman coefficient is known also as a range correlation. Okay. It involves ranking of the values in each variable. So basically you have two sets of data, two variables, and then you are ranking them. Okay, when ranking them means that, okay, this go number 1, number 2, and number 3, and that sort of stuff, then we'll see that in the example. Okay, it just introduce you through this thing first. Okay. So the degree of correlation between these two variables, which is ranked, okay, after they're ranked, it can be calculated using this formula. This is a simple one. Okay, this is a simple formula when there is no tie rank. So that means that there is no two number one. Okay. So it's like in Olympics, you can use this ranking. You can use this formula only there was one who get gold medal, one people getting silver medal, and one people getting the bronze medal. You can't use this formula when you get two golds and one silver and one bronze. Okay, that's called the tie rank. Okay, ก็คือเป็นลำดับเดียวกันนะคะนะเพราะฉะนั้นก็คือที่หนึ่งมีได้คนเดียวที่สองมีได้คนเดียวแรงสามมีได้คนเดียวอย่างนี้เป็นต้นนะคะ so if there was a tie rank, so if you have rank 1, two people have rank 1, you have to use the full formula for Spearman's coefficient to explain the correlation, which you can search the internet, and there are so many of them. Okay, instead I want you to get the idea of what is correlation and use the simplest things to calculate. Okay, so with this formula, you see that there is numbers there, that's why it's simple, because it has some fixed number, and the DI here. Okay, DI is the difference between ranks of the ith observation. Okay, you probably see this. You will see this in the example, and n is number of observation. Okay, so how many observation you have? Okay, so we can use this formula. You see that with the mathematical expression itself. Okay, if this number is less than 1, you get a positive correlation. But if this number is more than 1, you get a negative correlation. So correlation can be positive or negative. Another type of correlation is called the Pearson's coefficient of correlation. This one is as close as the R square as possible, and you'll see why. So this one is not ranked. Okay, Spearman coefficient, you have to rank the data and calculate the correlation, but Pearson's coefficient is working on the data only, and the full name is Pearson product moment correlation, okay? And as I told you, it's the most common feature of correlation. So it's more or less related to R square. Okay, I'll show you later. Basically, if you square this thing up, you get R square. Okay. Or if you take √2 of R square, then you get Pearson's product moment correlation. Okay. So the formula to calculate the Pearson correlation is this formula. You see that in order to calculate, you have to have, since this is correlation, you have to have two variables. One is X and one is Y. You see that? So you have to have an average of data of X. You have to have the average of Y, and then you minus the difference of the values, each individual values with the average. Okay, so anything with the bar on top are the averages. Okay, and this is the formula. Important assumption for Pearson's coefficient of correlation is that it has to have a linear relationship between two variables. Okay, this comes important as it implies also that if you are calculating R square when you fit the graph, fit the curve, R square works well only with linear relationship. If you don't have a linear relationship, R square doesn't tell a lot. There's something else that tells how good the data correlate. Okay. And another assumption is that one variable is independent, another one is dependent, and another one is independent. That means that one thing has to depend on another thing. That's why Pearson coefficient correlation also relates to the regression, which is the R square values. Okay, and see, this assumption is that the data set has to have a normal distribution. Okay. For the third assumption, it's we don't really state or talk about it that much, that the data has to be normally distributed so that you can actually use the correlation to explain the data set. Most of the time, we make an assumption that everything we use is normally distributed. Okay, but the important assumption is the one that makes it will relate to the regression analysis. Now, let's see the example on correlation. Okay, I hope that you have your calculator and stuff. Okay, so we can start doing something, and then if you have any question, that is the good way. That is the good time to ask. Okay, the first example is about the Spearman rank. Okay, so the Spearman's rank is this page. So it's a range correlation. It's involved ranking, putting people in number 1, number 2, and number 3, and so on. Okay, we see the Spearman rank correlation first. Okay, we have 9 students in physics and math. Okay, we have 9 students taking exam in physics and math. So that means that we have 9 observations because we have 9 students. Okay, and the two relationship between physics and math. So in this example, it says that, okay, the first student got this mark, 35 marks in physics, got 30 in mathematics. Second student get 23 in physics and 33 in mathematics. And the last student get 28 in physics and 31 in mathematics. Okay. What I want you to do is to try to calculate the Spearman rank correlation. So basically what we are trying to calculate here is to see whether people who has done well in physics will do well also in mathematics. พอเก็ตไหมคะมีนักเรียน9คนสอบ2วิชาฟิสิกส์คนแรกได้35กับ30คนสุดท้ายได้28กับ31แล้วก็ตามนี้ไปเรื่อยๆเพราะฉะนั้นการคำนวณ Spearman correlation เพื่อที่จะดูว่าจริงๆแล้วคือนักเรียนที่ทำคะแนนฟิสิกส์ได้เยอะจริงๆแล้วทำแมทได้เยอะด้วยหรือเปล่าอันนี้เป็นจุดมุ่งหมายของ rank correlation นะคะso I get you sometimes to think about what you should do. Okay, you can go back and forth to see the formula and probably try a little bit first. Okay, and if you don't know after like a few minutes, if you don't know what to do, then I'll come and then start taking you through. But if anyone can do, just go ahead. Okay, you can take this opportunity to go to toilet or anything or having a little break. That's okay. But we will come back and talking about this. Okay, I mute my mic, and if you have anything, you can put on chat. I have to go to toilet for a while too. Okay. โอเคเป็นไงบ้างคะ anyone wants to ask any question to start with first oh one thing that I need to tell you that we can use a simple formula sorry we can use a simple formula for the Spearman coefficient in this case okay because in physics everybody has a different marks mathematics also everyone got different marks so that's why we can use a simple form of the equation to calculate the Spearman coefficient correlation coefficient but if in real life okay people will get the same mark like if you have two people get 35 in physics 3 people get 8 in mathematics then you will have to use the full formula like I said here okay that you can find the full formula to calculate the Spearman coefficient มีใครสงสัยอะไรเกี่ยวกับตรงนี้ไหมคะหรือไม่แน่ใจว่าจะเริ่มยังไงดีหรือจะบอกว่าเริ่มแบบนี้ถูกไหม
สงสัยค่าดีค่ะอาจารย์
ค่ะเราเสียงเราเบาไปนิดนึงค่ะสงสัยค่า
ดีค่ะ
ค่าดีนะคะค่าดีเราได้ลอง ranking หรือยังคะ
ยัง
ถ้ายังเราเราจะมองไม่เห็นค่าดีค่ะอย่าเพิ่งก็คือถ้าเป็นแบบนี้แสดงว่ามีใครได้ลองทำ ranking บ้างหรือยังคะฮัลโหลมีใครได้ลองเริ่มทำอะไรหรือยังคะ Has anyone got the starting point somewhere if not okay the first thing that you should do is to rank okay that means that you have student number you should have mark in physics and mark in math okay so the first student number 1 get 35 in physics and 30 in math correct student number 2 get 23 and 33 student 3 got 47 and 45 student 4 5 6 7 8 9 up to 9 they get physics number 28 marks 28 and 31 after you have this then you can rank okay just let me go through you if you don't understand at any point you can just ask okay okay after this you should rank like say out of 9 students here people who get 35 what ranking is this student okay so you start ranking that means that the first person who got physics the highest physics who ranked number 1 in physics right so 43 is number 1 in physics then people who get 35 will be number 2 in physics oh no wrong 47 is 1 in physics 43 is 2 in physics 35 is number 3 in physics you do this for physics and math do you understand okay okay so For those who don't respond, I hope that you probably trying yourself right now. Okay. Okay. So this is a ranking in physics. Okay. Then you do the ranking in math. Okay, you do the ranking in math. So 49 is 1, 45 is 2, 33 is 3, 31 is 4, 30 is 5, 23 is 6, 7, 8, and 9. Okay, so once you see this, D is the difference between the ranking. So D of the student number 1 is -2, right? Then after that you square and then you get the D square. Up to this point, anyone has any question? มาถึงตรงนี้มีใครมีคำถามอะไรไหมคะ ถ้าไม่อยากเปิดไมค์ก็เปิดแชทพิมพ์แชทได้นะคะ so up to this point you calculate DI. DI for 3 and 5 is -2, right? This one is also is 2. This one is 1. 0, -1, 1, 1, 0, and 0. Okay, so you D square them. Okay, do it for yourself. I have the answer for you, but I just want you to try first. Okay. Okay, up to this point, anyone has any question? Not yet, right?
ตอนนี้ยังไม่มีค่ะอาจารย์
โอเคค่ะ Okay, I hope you are trying something for yourself while showing this thing to you, okay? So this is the part we are looking at right now. Okay, I think I blow up a little bit. Okay. Okay, up to this point, anyone get any number? Or just let me know if you have the same number as me doing like hand calculations. Or you don't know where which number come from. Any question? Or if you have done the calculation and get the answer, please type in chat and say that you are done and you get the answer. Okay. Yep. Okay. So Epic get the same answer as I show. Okay. So at least you know how to calculate the thing. Okay. Maybe just wait for a few more people, and if you want me to wait, just let me know because we still have like a little bit of time. Okay. Okay. Wait for a bit. Okay. So 3 of you got 0.9. Yep. 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 Okay. So it seems like everybody know how to calculate. Okay. You get 0.9. What I want to tell you here is that since you got 0.9, okay, you got 0.9. So looking at the formula, okay, looking at the formula itself, it is 1 minus something, right? And since it's positive, so that means that students who are doing well in physics tend to do well in math as well. Okay, so if you got good mark in physics, you are likely to get a good mark in math. So that's what it says. But if the Spearman coefficient is 0, okay, is 0 or 0.005, for example, okay, so that means that it doesn't tell that if you get good mark in physics, you will get a good mark in math. So that's how it is presented. Okay. Or if you have the Spearman coefficient to be negative 0.9 instead of positive 0.9, that would mean that if you get a good mark in physics, you will get a bad mark in math because it's a negative coefficient. Okay, so that's how the Spearman's coefficient is used. Okay. You might not see how it could be applied to your life at this stage, but like for me, sometimes it's pretty useful also to analyze like the performance of the students and that sort of stuff. All right, before we go to the second question on Pearson's coefficient, anyone has any question to ask?
Yes, Ajahn.
Yes.
I want to ask a
Yes.
question.
Yes.
You said that if the value is 0.005 is bad, it is a bad number because the student that gets lower physics doesn't mean they get lower in mathematics, and if it's negative value, it's also bad. What if the value is 0.6? How do we determine is it good or is it bad?
Okay. The point is for correlation, there's no good or bad. It just said that if you have high values, that means that the two values are very correlate. There is no set point where more than 0.5 have a good correlation or less than 0.1 is a bad correlation. It just tells you the degree of how correlate they are. You get what I mean?
Yes,
It just tells you how correlate they are. The higher the values you get, the better correlation it is. Okay. For the simple formulation that you see here, you might notice that the best thing that could happen, or if there's a sort of like a perfect correlation, DI will be 0, right? People who get first in physics get first in math. People who get second in physics get second in math. People who and so on. That is when you get the DI of 0. And if you have a DI of 0, this one goes to 1. So it's very closely related. But to say, oh, it's 0.4, it just tell you how strong the correlation are. Does this answer your question?
Yes, Ajahn. So for the first question, if the value is 0.5 or 0.4, it's not on 0.9 because it's higher.
If it is 0.5 or 0.4
Mm-hmm.
instead of 0.9, so it means that it has some correlation, just that the correlation might not be that strong.
I see. Yeah.
So there's no
Thank
clear
you.
cut.
Yeah.
So bad or good. But if it is like 0 or very close to 0, whether it's positive or negative, it just say that, hey, it's almost has no correlation.
Yeah. Okay. Thank you, Ajahn.
Okay. Oh, another thing that the EPIC ask could raise another question of, so in that case, how would I say that it has or not have, whether it has a strong or weak correlation, or if the performance, the correlation of, say, if you have 2 classes of year 5 students and one class and another class has a different correlation, how could you tell whether one class has a better correlation than another class, or whether it's a strong or weak correlation? For this thing, I think that you probably have to apply sort of like the inferential statistic to make a decision whether things are different. But really the Spearman correlation mainly it tells you like the strength of the correlation. Okay. Okay, so for example 2, okay, so I passed the Spearman's, okay. So for question 2 is a different type of correlation. It is now the Pearson coefficient of correlation. Okay, you see that the type of data or how the data is arranged is sort of like is different from Spearman rank correlation, because you are finding the correlation in a different meaning. Because Spearman's rank, you want to see whether if this one perform well, whether if one perform well in physics, would it perform well also in mathematics, and if it is, how strong it is. Okay, but the Pearson coefficient, okay, is representing something else. Okay, it's representing something else. It's not like for this one, if you have for this one, well, you can use Spearman, but for the Pearson coefficient, it's more like you want to find the correlation between age and glucose. Okay, using Pearson coefficient. If you're asking me whether you can use Pearson coefficient in calculate in this set of data as well, you can. I'll talk about it later, but for the sake of understanding the calculations, I want you to try to calculate the Pearson coefficient using this data. Okay, so if you go to the Pearson coefficient formula, okay, if you go to the Pearson coefficient formula, you have seen that x and y, right? And the average of x and average of y. So I put here that age can be considered as x data, and glucose is the y data. So you have 6 subjects, and each with different age and glucose. I want you to try to calculate the Pearson coefficient. So basically this one will be x1, x2, x3, x4, x5, and x6. This one will be y1, y2, y4, 3, y4, y5, and y6. And according to this formula, you have to find the average. This is the arithmetic average of x and y. So the first approach would be finding the average ages and average glucose concentration. Okay, anyone has any question at this moment about calculation? Okay, just because we have about 5 minutes, I'm just going to show you the so hold on, stop share and sharing another thing. Okay, so this is Pearson coefficient in the examples that I'm giving you right now. Okay, so basically you have age and you have the glucose blood level, and then like I told you that the first thing is to find the mean, right? Then you subtract each individual x and y with its respective mean. Then you have x minus each of the x minus x is average and each of the y minus y average. Okay, then each values do you just follow the formula. Okay, you just follow the formula and then do the calculation. What I want to show you is that this is the R that you will get, which is the R for Pearson's coefficient, which is 0.52998, about 0.53. You can note this number down just to check for your note this number down to check your calculations. Okay, and what it says here, okay, what it says here, since the Pearson's coefficient, okay, is the one of the assumption that they talked about is that one has to be dependent and another one has to be independent variable. So we can with the Pearson correlation we can say that whether the glucose concentration depend on age. Okay, it looks strikingly similar to Spearman, but for Spearman, if for example, you can actually use the Pearson or Spearman to calculate using the same data set that I give to calculate Pearson or calculate Spearman. You can choose, okay? But for this one, if you calculate Spearman, you get this, and then it will just say that if your age is independent variable and the glucose level is dependent variable. For the Spearman's correlation, it will say how dependent the glucose is on the age. Okay. Actually, what I have done here to show you that the same data can be done using the same data set. You can use either Spearman or Pearson's is buying this example. Okay. The part that I highlight here is when I'm using the same data on this page, but calculate Pearson coefficient. Okay, so the Pearson coefficient is a little bit higher, but within the cross range, like 0.995, but Spearman coefficient is 0.9. but it shows a strong relationship. So basically, if the Spearman coefficient, you say that, okay, if you are doing good in physics, you are likely to doing good in math. But with the Pearsons, it means that there are a strong relationship between people getting a strong relationship of the mark you get between physics and math. So it's just a two different way to interpret the data. Which one is okay? It depends on how you want to express your data. The point is that with the Pearson relationship, you are, like I told you, that is very closely related to R square, because normally I'm plotting this one just to show you that if I plot the graph like we do normally for X and Y, this is what you get, right? And then you see that the relationship could be a linear relationship, and then you fit the graph, and with the trend line showing the R square of 0.9022. Okay, let's see, like this one. Okay, this is what normally you do, right? You add the trend line, the linear trend line, and then you display R square. You see that the R square that you get is 0.9022. Okay, when I say Pearson correlation is very closely related to the R square when you do the regression, because if you square the Pearson coefficient, you get exactly the same R square when you do the regression. So that's why I'm saying that the Pearson, the R square values when you fitting the trend line is closely related to Pearson R square. Okay, but Spearman coefficient is different. You square this one, you're not getting the R square values here. It can be confused because the R and the R square also, right? But just want you to know that if you are doing Pearson, is related to the R square in the regression. But with the Spearmans, it's ranking and just tell you like the likelihood of getting something good, and that thing is good. But this one is a correlation, how, like for this one, it will be how the glucose related to age. Okay, so the different thing is a ranking. But if you ask me, can I do the Spearman correlation in this one too? Yes, you can. Yes, you can. Okay, so choosing the type of data and what correlation to use is also another thing that you have to think about, the suitability of presenting your data. All right. Okay. I hope you get all those numbers that I told you. So if you want to go back and try to calculate yourself, you have some answer to check upon. Okay, so that's it for the lecture today. Next lecture we have on Thursday afternoon, right? We'll talk about the R square. We'll talk about the R square. We will talk about the curve fitting and what we should use for the curve fitting, or whether the R square tells you everything that you want about the curve fitting. Okay, so don't try not to miss the next lecture, which will be on Thursday afternoon. Okay, and at this point, if you have any question, you can put the post on class on in Google Classroom. Okay, just leave the question there. I am likely to get. I will go and have a look at the question, and if there's anything, I could prepare the answer for you when we meet next time. Okay. All right, so I think that's it for today. Thank you everyone, okay, for participating, and I'll see you on Thursday.
ขอบคุณครับอาจารย์
ขอบคุณค่ะอาจารย์
ขอบคุณค่ะอาจารย์
อาจารย์
Okay ค่ะ ขอบคุณค่ะ Yeah, you can
อา
leave the
จารย์
room.
คะ
ค่ะ
พอดีหนูวันพฤหัสหนูมีฉีดวัคซีนวันเวลา11 โมงค่ะ บางออนองค์อาจจะเข้าช้านิดนึงนะคะ เผื่อกลับมาไม่ทันใช่ค่ะ
ไปฉีดเซนทรัลใช่ไหม
ใช่ค่ะอาจารย์
ออนองลองไปเร็วกว่ากำหนดนิดนึง บางทีคือรอบเช้าเขาจัดการเร็วเขาจะเรียกเร็วขึ้น
อ๋อ โอเคค่ะ
อัน
อา
นี้
จารย์ขอบคุณค่ะ
แต่ก็รับทราบนะคะ ก็ไม่มีปัญหาอะไรค่ะ
ค่ะอาจารย์ขอบคุณมากค่ะ
จ้าโอเคค่ะ สวัสดีค่ะ
สวัสดีค่ะอาจารย์